Math 1428, alternative delivery for 23rd March of 2020. And you all know what this symbol means. So do some. Today we're going to cover chapter 4.3. We're going to talk about polynomial division, the remainder theorem, and the factor theorem. So these are the learning objectives that we will cover in this lecture. Now, sometimes students find they don't remember everything that they learned previously about long division, either with numbers or polynomials. And so here's some remedial links that might be useful in the Learning Commons if you need to go back and review some of this stuff. I'm going to, in what follows, assume that you're good with these kind of concepts. When we divide one polynomial by another, we do get a quotient and a remainder. A really important fact for you to make note of is if the remainder is 0, then the divisor is a factor of the dividend. And we'll do some examples of this and see what this means. So let's consider this function, and we're going to use long division to determine whether each of these is a factor or not. So what this means is we are going to be dividing that f of x by, in part A, x plus 6, in part B, x plus 1, and in part C, x minus 4. So go ahead and do these divisions, and then we will come back and compare notes. So pause now, do the work, and come back. So you see, when we divide, and we want, again, we want to determine whether each of these is a factor of f into x to the 4th plus 8x cubed plus 5x squared minus 38x plus 24, we get a remainder of 0. That means that x plus 6 is a factor of f of x. Over here, when we divide x minus 4 into the same f of x, we do the work and we get 720. Since the remainder is not 0, that means that x minus 4 is not a factor of f of x. Just like in arithmetic, to check a division, we multiply the quotient by the divisor and add the remainder to see if we get the dividend. And so this is kind of a check that we have, and in addition to being a check, this is the basis for the next theorem that we're going to discuss. This is called the remainder theorem. Here's what it says. If a number c is substituted for x in a polynomial, then the result f of c is the remainder that would be obtained by dividing f of x by x minus c. Well, here's why that is true. If we divide f of x by x minus c and get a quotient of q of x, then f of x must equal x minus c times q of x plus r. So if I plug in c for x, I get f of x here, but c minus c is going to be 0, so the only thing I get on this other side is r. That really is the proof of this remainder theorem. Now, what this means, though, is that another way to evaluate a polynomial is given in this theorem. And so what we can do is we can do long division and look at the remainder. And you will be asked to evaluate polynomials this way in future assessments in this class. And you're going to be doing this without calculators. So please pay attention to the examples doing this. And one big tool we're going to use for these kind of divisions is called synthetic division. Now, synthetic division only works when you have linear divisors. That means the divisors have to look like x minus c. Now, here's what you do. Here I have x minus 2, so what I'm going to do is I'm going to take 2. And the only thing I'm going to write is the 2 right here. And then, instead of writing all these x's, x cubes and x squareds and x's, all I'm writing is the coefficients. So that is going to be 4 minus 3, 1, and 7. And instead of doing synthetic division like this, all I need to do is the following steps. I pull down the 4. I take 4 times 2 to get 8, and I put the 8 here. And then I add up and down. The SIGNs matter, the signs matter. And so when I add these, I get 5. Then I take this 5 times this 2 and get 10, and I put the result here. Add down, and now I have 11. Then I'm going to take 11 times this 2 and get 22. Adding up and down, I now get the remainder, and the remainder is 29. And that is what f of 2 is. Now that might have seemed like that took a while, but actually that calculation is little multiplications and little additions and can be done very rapidly. It is also important for students to realize that when you have finished that, since we started with a cubic, but we divided it by a linear term, we now have a quadratic term where these are the coefficients. It is also important for students to realize when you use synthetic division, you write a 0 for a missing term in the dividend, and we'll have examples of that later. But now I'm going to ask you to find the quotient and remainder for these problems, and let's just try in this case problem number 16. So pause, and I'll be back in a bit. Pause, and I'm back. Let's look at problem 16. So doing problem 16, notice that I had x plus 3, so I had to put a minus 3 here. And remember that I said when we skipped powers of x, we had to put zeros. So we skipped 2 powers of x, so we have to put 2 zeros there to do the calculation. And now we will do this. So we bring down the 4. 4 times minus 3 is minus 12. Add up and down, you get minus 12. Minus 12 times minus 3 is a positive 36. I add up and down, and I have 36. 36 times minus 3 is minus 108. I add up and down, I get minus 110. And minus 110 times minus 3 is a positive 330. I add that, and I get 335. So that means that this division, there's 2 results. One is that my quotient is 4. It was x to the 4th, but now it is x cubed, minus 12x squared, plus 36x, minus 110, and the remainder is 335. Here's some additional problems using synthetic divisions, but here we're using it just to find the function values. So let's look at problem number, let's say 26. And what we want to do is we want to find what is f of minus 10, f of 2, and f of 3. Let's, for our sake of doing this, let's just focus on finding f of 2. One thing that you should notice before we start is we skip x cubed, so we have to insert a 0 there when we do synthetic division. Pause, do the problem, and then come back and we'll look at the solution together. So let's pause now. I'm back, and let's look at substituting 2 in. As we talked about, you needed to put a 0 in here, and we're trying to find out what is f of 2. So f of 2 is going to be, I bring down this 2, and it's 2 times 2 is 4. Add up and down and get 4. 4 times 2 is 8. Add up and down and get 9. 9 times 2 is 18. Add up and down and I get 8. 8 times 2 is 16. I add up and down and I get 17. That means that in this case f of 2 is 17. And there's some other examples here that are useful for you to check. Now Another theorem is that to figure out whether something is a zero, what we have to do is the remainder has to be zero. So we can pick these, and this time, since the imaginary roots can be, the imaginary numbers can be roots, and this is a good opportunity to review. Let's look at problem 35, and we're checking, is I a root or is minus 2i a root? So pause the video and we'll compare notes in just a bit. So pause now, do the problem, and then come back. I'm back. Let's look at number 35. Okay, so we put I here, and the coefficients are going to be 1, minus 4, 4, and minus 16. But this time I have to keep in mind that I squared is minus 1, and I have to remember how to do these calculations. That's why we spent time last chapter learning about these calculations. So I started bring down the 1, and 1 times I is just I. So when I add I to minus 4, I get minus 4 plus I. But now I'm going to take minus 4 plus I times I. You probably don't do this in your head, but what you will get is minus 4I minus 1. I add up and down, and I will get 3 for the real part and minus 4i for the complex part. Then I will take 3 minus 4i times the I again, and I will get 3i, and now it is plus 4, and so when I add these I get minus 12 plus 3i. So you see, when I put I into G of I is going to be minus 12 plus 3i, and that means that since that's not 0, I is not a 0. Now if you do the same kind of calculation with minus 2i, you find out that you do get a 0. So since G of minus 2i is equal to 0, minus 2i is a 0 of G of x. And we can tie these together with factoring as well, because if f of c is equal to 0, then x minus c is a factor. That's really stating what we said before. And so that enables us to answer a different kind of question in terms of factoring polynomials. And let's try problem number 41. Now, one thing that is a little difficult about this is you have to spend a little bit of time guessing or thinking about what might be some roots to try. But once we find one, we can knock this down from being a cubic to being a quadratic, and we can handle quadratics much more readily. So let's try 41. Pause and return in a bit when you've done your work. Pause now, and we're back. And we're doing number 41. Well, if you try 1, you'll see that it's not equal to 0, so that didn't work. But if you try minus 1, you see that minus 1 is a 0, and that means that x plus 1 is a factor. So we know that f of x is equal to the factor that we just found, x plus 1 times what's left. Now, this was originally a cubic, so now as a quadratic, it is x squared minus 7x plus 10. We can factor this into x minus 2 times x minus 5. So now we know that the full factorization is x plus 1 times x minus 2 times x minus 5 is equal to 0. That means that x is equal to minus 1, or x is equal to 2, or x is equal to 5. Now, there were a number of concepts that got talked about here, and connecting them together does make a lot of sense. And so these statements all really mean the same thing. Minus 3 is a 0 of f of x. F of minus 3 is equal to 0. Minus 3 is a solution of f of x equals 0. Minus 3, 0 is an x-intercept of the graph of f. 0 is the remainder when divided by x plus 3, or x plus 3 is a factor of f. That's 6 statements that are saying the same thing, and you want to understand that these concepts are so intimately connected. We are being asked here to sketch a graph of a polynomial, and we've graphed them before, but now we have an improved understanding of ways to find the roots for these functions. Let's do problem number 54. So please pause, think about it for a while, and we'll play. And as you pause, please realize that I'm going to ask you to graph it and fill out a table. So here we go. Pause now, and I'm back. Okay, so we can immediately tell from before the end behavior is going to be a frown, and we can test some values and find that in fact, and here's the work that does that, that -1 in fact is a root twice. So it's a double root. So we do it once, and then we do it twice, and now what's left after doing that division twice is it is -1 for -4. That means that the quadratic that is left is minus x squared plus 4x minus 4. So you see, and by the way, this factors nicely. This is going to be x plus 2 whole squared, and then a -1 in front of that. So it's minus parentheses x plus 2 whole squared, x minus 2 whole squared, excuse me. So both -1 and 2 are double roots. That means the picture looks like this. And those are the x-intercepts and the y-intercepts, and we know the end behavior, and we can use our calculator to determine approximately the coordinates of the relative minima. Pretty cool, huh? We really did quite a bit with this problem. So now more than ever, time is precious. Each day must count. Do the math, it will make you strong. Take care.